the overview of the runtime stack. So what is the runtime, right? So I think hopefully the audience knows that we have our own hardware, right? Both the chip and the hardware box, right? So in order to be able to interact with the hardware, you need something like a mini operating system who actually can manage the hardware and the software interface for you. So that's what the runtime stack is for. So we have a scalable high performance runtime stack for our DataFlow distributed system. So as I said, it's like a mini operating system. So it manages the compute, manage the memory allocation, and also manage the the I/O interaction with the hardware through PCIe and some other like networking fabric, fabric-based networking stuff. And the part of runtime's responsibility is to be able to run an application. Right, so I think we can talk about the compiler part. So once your application goes through the compiler, it will generate an executable. Now, in order to run an executable, you will need some software pieces to be able to actually run it. So that will include set up the application, get all the necessary hardware resources, and then actually you do some scheduling and execution on our RDU to actually run your application, and eventually also tear it down once the application is done, so you can collect the allocated resources and also maybe do some cleanup at the end. So right now our runtime supports different operating systems. So we have like Ubuntu 20 and also Red Hat 8.5, and these things evolve when we work with small customers. And also we have minor version backward compatibilities for all the runtime interfaces, so that if you have a newer runtime with some older, let's say, compiler, as long as they're within the same major version, I think the application will still work. So this is kind of the core feature of the runtime. So I don't want to overwhelm people. So let me just briefly touch the surface a little bit. Right, if you look at the the graph, the yellow part is basically your, you can call it the host of the whole system, right? So it can be a bare metal CPU based system. It can be something you run in a virtual machine or even a container instance. Right, so within this box, you have the blue one, which is what you run on the host, the CPU. And then you have the pink one, which is our, what we run in the RDU. And your application will, be launched on the host. And then, the runtime stack basically will manage, the setup, the run and tear down on the RDU, the pink boxes on the RDU for you. And then if there's any necessary data transfer, data movement between, host and RDUs, runtime stack will also handle that for you, so that when you run the application, you have the necessary data available, on your RDU side. In addition to a single node, we also have connect fabric between these yellow boxes, right? So you see we have like host connect fabric where different hosts will connect to each other, and also we can use the host connect fabric connect to external remote storage and any other like external compute nodes. And also we have the pink box, the purple box, which is the RDU connect fabric, which will connect the RDUs directly. So if there's any communication need to happen between RDUs, it will go through that fabric in a more direct fashion. So overall, the runtime stack supports model parallel within a node, which is the little box here, and also we support like data parallel within and also cross node over the purple cloud block, which is the RDU connect fabric, and also like in addition to like the run the connection part. We also support RAS, which stands for like reliability, availability, and service ability, and also like external compute node, external storage node, and a bunch of other tools like debugger, performance profiling tools, and configuration and system management tools for you. So I will deep dive into each of them a little bit in the following slides. So feel free to ask me the question, but this is basically where it gives you a very high level picture of what the runtime stack will do. So runtime stack also support like multi-tenancy and multi-user, right? So we have like RDU level virtualization through SRV, and also support OCI compatible containers like through Docker or Podman. And in addition to multi-tenancy, we also support like multi-users. So we can support up to 8 parallel applications running simultaneously on a node. And when you run that 8 applications, we'll provide like mutual exclusive compute, memory, and I/O resources among each of them, so they will not step on each other, and it will give you that level of isolation and security. So this is, I won't deep dive into the slides, but this slides basically show you that we have, a way to run very low latency inference through the runtime stack. So, usually when you develop your application, you probably will first use something called, software orchestrated multi-session graph, right? So that will allow you to run your application in a more flexible way. So if there's anything wrong with your application, then you can debug it very easily. So because it's controlled or orchestrated software. So once you reach a point where your application, is pretty settled, you already debug it very well, then you can move to hardware orchestrated multi-session graph. So this is something runtime actually work with compiler together. So when you generate your graph, you actually have a knob to decide whether you want to generate your graph in a software orchestrated way or hardware orchestrated way. So once you have the hardware orchestrated graph, it will give you better performance, especially better latency. So when you actually deploy it in your production environment, it's the best fit. And we support like model parallel across multiple RDUs. So we can support up to running the same model up to on 8 RDUs over the PCIe fabric, and also the communication is done through the compile time. So basically any communication between RDUs, it will use our proprietary P2P protocols to transfer data between RDUs. We also support distributed training through data parallel, right? So the previous slide talked about like low latency inference. So this part particularly talk about training. So I think all of you know, right? Training these days, like machine learning models can go very big, and one node is definitely not enough. So in this case, you have to run your application in a distributed fashion. And data parallels is actually one of the most popular and most efficient way, to run your training in the distributed fashion. So we support, using the network fabric to communicate between RDUs in order to run the distributed training in the data parallel fashion. So it can cross RDUs within a node. It can cross RDUs that cross the RDU node boundary, and even cross RDUs across the rack boundaries. And we'll support like more than 1,000 RDUs over the RDU and over the RDMA transport. So we have our own collective communication library, our own like CCL libraries, basically to achieve this, right? It support a various of collections of primitives such as like all radios all gather, send, receive, things like that. And we can support like mixed precisions, all radios as well, and with some optimizations like grading groupings and synchronization overlap to bump up the overall throughput of the data parallel stuff. In addition to that, we also support like different topologies, right? So I think some of the most popular ones, such as bidirectional rings, all-to-alls, and also hierarchical all radios, will give you different throughput performance over the network fabric based on the characteristics of your model. So we support all of them, and we have an algorithm to automatically pick the best one for you to some extent. So this is like the hassle-free part. And in addition to that, we also have the RDU Direct, which is our in-house transfer protocol, which can move the data between RDU memories directly instead of going through the x86 host. So in this case, you can save multiple copies by to improve the data parallel performance. So this is actually, this slide is actually talking about like, data transfer in general, right? So, when you move data, I think like in the previous slides I mentioned, there are usually two types of data movement you need. One is moving the data between the host and the RDU, and another one is moving data between different RDUs. So we actually support both, right? For the host to local RDU data transfer, we support like DMA, we support different types of DMA, like direct DMA and scatter-gather DMAs, and also we support like direct memory copies through the PCIe bar the configuration space. So it depends on which one you need, because they have like different trade-offs. So it depends on like what best fit your application. We have these options, and in addition to that, I just mentioned we have RDU Direct, which will allow you to move data between DDRs of different RDUs directly, by through bypassing the host completely, so that you won't have like multiple copies of the data movement when you want to move data in this case. If you guys remember, right, when I present the core features of runtime, there are two bubbles, right? There's a host, connect fabric, and there's a host connect fabric, and there's RDU connect fabric. So you use this fabric for, let's say, RDU Direct, like that's the one I just mentioned, and you can use the host connect fabric to actually do storage and external compute. So one of the use case of that is actually remote execution. So this is something we have been working with, like different national labs. I think we presented to some folks from Argonne actually once. This is a high performance communication and execution framework that actually will allow you to move data and run application from a non-SambaNova node, which we call remote client in this case, on a SambaNova node. So this framework actually contains both the control plane and the data plane. So, whenever you want to run something, you actually will, launch the application on a non-SambaNova node by through, our own remote execution client. And also, once so this client will connect to the server that's running on the SambaNova node, and then, launch the application, kick off the application on the RDU. So once that is done, you actually can, stream the data from the application through the client to the server constantly. And the server will just constantly stream the data into the RDU where the application runs. So in this case, it actually will allow you to run something really quickly on SambaNova node without logging onto our node directly. Because I know there are cases where you may have limitations that your application or your data comes from your own compute node. And you need to move the data and application onto our compute node later, right? So this framework actually will allow you to do that in a very high performance and high throughput fashion. So this is one of the framework that we actually have, and we support like the synchronization mode where it's easier to debug, and we also support asynchronization mode where you can overlap the data transfer with the execution so that you can get like better throughput performance out of it. So I mentioned, so far what I mentioned have been mentioned is all about how you run different things. But in order to use our system more thoroughly, you also need tools. You also need a bunch of like reliability related stuff in order to maximize the capability of our system. So runtime team actually also provide those tool chains as part of our stack. So we provide hardware fault and error management as the way for the system reliability, availability, and serviceability control. So we provide the records of the errors, and also records of the fault hardware, and also like recovery suggestions if anything bad happens. and we have this very nice tool interface for you to use. This is especially for system admins, but in theory, any ordinary users can actually use it to actually check what's going on with the whole system. Anything wrong happens. So you see, this is a snapshot, of the output of this tool. On the rightmost column, it shows you, a list of the components we have. Different PCIe channels, different RDU tiles, and also different DDR memories or DDR DIMMs. And on the rightmost two columns, it shows you the current status, of the hardware, and also, whether they're usable state or not. So it gives you a lot of visibilities into what's happening on hardware. As I mentioned, we also have tools to improve the diagnostics and debuggability when you actually run something, right? Because what Yuan showed you is when you run the compiler, when you use the compiler to compile something, they have a bunch of tools and logs to help you debug the issue. And what runtime team provide is tools around what happened when you run something. So we provide exceptions and syslog based logging system for you to actually know what's going on when I run something, right? If there's an error of this exception happens, we have both the logs printed to the console and to the syslog based files to give you that information, like what exactly happened. And we have different levels of logs, info, debug, error, notice, etc. So it can there's always one flavor to fit your particular use case. We also have a bunch of tools as to provide the diagnostic capabilities, right? So if you run something and turns out the performance doesn't meet what you expect, you will need some dynamic information to know what the bottleneck is, like where I spend a lot of time. So in this case, we have profilers to give you end-to-end performance breakdown. We also have a bunch of statistics tools to give you more insight into what happened to the compute unit, what happened to the memory, and what happened to the I/O. So you will know whether I'm stuck because my DDR bandwidth is not fully utilized, or I'm stuck because my I have a heavy PCIe traffic, so PCIe throughput becomes the bottleneck, or I spend actually a lot of time just running my application. We also have new debuggers, which we call the Graph CLI, that will allow you to do some live real-time debugging. So it supports the the capabilities such as the breakpoints, step through, and tensor value picking, etc. So you will be able to pause your application in the middle and know what's going on if something is wrong or something didn't happen as you expected. I believe this is the last slide of my presentation. So I don't know whether you guys have any question that you want to ask. Okay, so I'm looking at the chat right now. I think the question is the inter-RDU and inter-node bandwidth latency used within a model execution, especially for inter-RDU RDMA calls. I'm assuming we may have cases where latency is important, not just a large message bandwidth. Also, actual values would be nice to see if RDU is driving the comms, it is up to the DMA engine in it, or the PMU driving the bar access to small messages. Both, I would like to hear both values. Yeah, so I don't have any value on top of my head right now. I can definitely find it for you and share with you later. Right. The thing is this, right? If you look at our so I mentioned, right, when you run the model parallel, we actually use our P2P protocol over the PCIe. So this will actually move the data. This has the capability to move the data directly between PMUs and the DDR of another RDU. So in this case, this is something that is sort of driven by both compiler and runtime. So compiler will at the compile time decide what would be the best collections of the PCIe channels, and and runtime will pick those PCIe channels as much as possible if we can, based on the instruction or the information provided by the compiler. And so in this case, this is like pure, P2P based stuff. Now, when we move to the fabric, this is where compiler is not part of the picture now, and you will have the capability to move the data between one RDU's memory and another RDU's memory. But when we talk about memory, we mean DDR in this case, because RDMA devices don't have the access to the PMU directly. So in this case, we just move the data, like we use like IB or Rocky, to move the data between the RDU memories. Yeah. Okay.